In our last lecture I have pointed out that Kepler's first law, that planets move around the Sun at an orbit resembling an ellipse, is the new law of nature. Kepler found that out because Tycho observations were off from a circle by mere arc minutes. But Kepler's second and third law brought a whole new level of precision. Galileo experiments made precision all the rage. Then came Newton's synthesis. Our man of the hour, Johannes Kepler, was a sickly child that lost his good eyesight as a teen due to illness. Fortunately for us, that was after he already fell in love with astronomy. Still, he couldn't observe anymore and had to rely on other people's data. He excelled in math and astrology. Astrology is the ancient art of casting horoscopes. That has since been discarded as non-scientific, but at Kepler's time, Kepler would use much of his career trying to relate planets, moons, and sun position with weather and how they influenced everybody's life. That actually led him to science. And that was not even his strangest idea. At age 30, he taught math in a small private school. He started corresponding and collaborating with Tycho Brahe, one of the most unlikely collaborations in history. For one thing, Kepler hated Tycho's weird model, and Tycho hated Kepler's recently published model with the Platonic solids holding planets in place. Both had the integrity to accept each other's failings, otherwise science would have languished for hundreds of more years. Kepler lending his hand on Tycho Mars observation made it possible for him to come with his laws. It was no coincidence that Kepler did not deduce the elliptical orbit of planets from observing Mercury that I've shown you the last time. These were not made available to him at Tycho's death. Remember that, guys. Observations from anything to anything is what makes things go round. Let's look at the second law of Kepler again. Kepler assumed that as the planet gets closer to the Sun, it moves the fastest. His law states the radius vector, the line between the planets and the Sun, sweep equal area in equal times. Now that's a physical law. This is basically the first physical law of the new scientific age. Nowadays we can measure these speeds relative to planets by shooting radar at them, the same way police cars do. A consequence of Kepler's second law is that Earth is moving a tad faster when it's closest to the Sun, which happens to be on January 4th. Notice, not in the summer. Remember, seasons are a result of Earth's tilt, not of the closeness or furthest we are from the Sun. Well, as a result, what happens is that on January 4th, the day on the equator, remember on the equator the days and nights are equal, but not exactly, because when we're closest to the Sun on the equator, the days are just a tad longer, as you can see from the picture below. Now, rather than having circles upon circles, epicycles, equants, etc., Kepler had the planets moving faster when closer to the Sun according to his second law. His mathematical prowess was then used for his third law. A modified average of the distance from the Sun is called the half of the major axis of the ellipse. This is the quantity in AU. When you take that and cube it, AU, by the way, is the average distance from the Sun, or astronomical unit. When you cube that number and you take the square root of it, you'll find the period in years. Earth's 1 AU from the Sun. Cube it, take the square root, you'll get 1, that's 1 year. Other planets work the same way. For example, take Jupiter's distance and cube it, you'll get 140, and then you take the square root of that, and that's about roughly 12 years. This neat trick is how we found out about extrasolar planets. Not only that, we found out how far they are orbiting their actual stars. More on that next Tuesday in class. After Kepler came up with his laws, a guy by the name of René Descartes, the same fellow that came up with I think therefore I am in philosophy, said, heck, the planets are moving faster when they're nearest the sun because there's all sorts of eddies, basically a lot of eddies right next to the sun, and the further out you go, the less and less eddies there are. That's why they influence the planets more when they're closest. Newton actually took that idea and said there's nothing in between the sun and the earth, there's nothing in between the sun and the planets, there's only gravitational action at a distance, and that is where our understanding of the universe was, at least until Einstein. Isaac Newton was perhaps the greatest scientist of all time. His father was a farmer that died before he was born. Newton was born a preemie, premature and small. His mom remarried shortly afterwards to a clergyman that Newton hated. He never studied math in his regular pre-university education. In Cambridge University, they taught Aristotelian and ancient Greek math and science, so he taught himself the works of Copernicus, Kepler, Galileo, and Descartes. He then proceeded to invent physics used by all civil and mechanical engineers that were around himself. He also co-invented calculus with Leibniz, co-invented modern optics, and the marriage of physics and astronomy called, astrophysics. He himself was never married. Not to be bored, I guess, he became the head of the Royal Astronomical Society, and in that role made the life of other scientists such as Robert Hooke and Leibniz hell. He was the head of the Royal Mint, making money. He was actually working as a detective to help convict forgers. And they hanged and quartered the forgers that he found. He was a prolific theologian that rejected the worship of Jesus as God, but strongly believed in a benevolent Christian God. He spent half his time on alchemy, the field of study that tries to turn lead into gold. But we have still limited information of many parts of his life. Newton's universal gravitation was a synthesis of the fact that the sun is acting on the earth and the earth is acting on the moon. As a result, he assumed that the earth is acting back on the sun and the moon is acting back on the earth. Taking that into account, he invented universal gravitation and Newton's famous three laws. Newton's three laws are actually not laws that were invented or found out by Newton, at least not the first and the second. The first law was first discovered by Avicenna or Ibn Sina, an Arab scientist in the 10th century in the area between Iran and Iraq. Galileo then rediscovered it and started the second law. The first law is that things keep on moving if you don't act on it. In empty space you don't need to push anything for it to keep on moving. The second law is that objects do speed up if you act on them. So in same empty space, if you get the rocket to fire, it will not keep the same speed. It will either speed up or change direction. And the third law is that the force by an object on another is the same as the force by the second on the first. For example, first, the force by the sun on the earth, same as by the earth on the sun. So why is the sun not moving much? Because it's much more massive. Same with the moon. The moon is going around the earth. Why is the earth not moving around the moon? Because it's much more massive. However, lo and behold, some influence by the moon is detectable. For example, the tides. This is one of the very few equations that I will include in this whole class. Another one that will come much later would be E equals mc squared. but don't expect more than one or two other equations throughout. This equation is called the universal law of gravitation by Isaac Newton. What it says is the following: the force between two objects is proportional to mass 1, uppercase M, times mass 2, lowercase m, times some number divided by the distance between them squared. That's exactly the same as we had in the previous slide. Now this is a relationship that held true until the last 100 years. 100 years ago, Albert Einstein figured out that this equation should be modified. But from the 1600s and until 1915, this universal gravitation law held supreme. This is the equation that is implicit in all of the laws of the previous slide. Not only are tides a result of Newton's universal gravitation and the three laws, but also the precession of Earth's axis of rotation, the reappearance of comets and asteroids, Earth's oblateness where the equator is a little bit fatter than the poles, and many other things. For example, let's look at the tides. Assume that Earth is the green circle, filled circle, and that the blue is the ocean surrounding the Earth. Earth spinning around its axis, and NP here stands for the North Pole. We're looking from above the North Pole. Go to the next slide. Now note that the side of Earth closest to the Moon experiences just a tad more gravity than the middle of the Earth and the other side. So the oceans closest to the Moon hump up, the Earth itself moves within the oceans, and the other side of the ocean is left behind. Therefore, every time Earth spins on its axis once, which is one day, we're going through two tides, pretty much. It's a little bit off because the Moon is going around the Earth the same wide time that the Earth goes around the Sun, and as a result, it's really not every 12 hours, but every 11 hours in 50 minutes or so that we get high tide. The Sun also makes for tide. So when the Sun and Moon are working together, either in full moon or in new moon, we get very high tide and very low tide. And in the first and third quarters, we're gonna get not as high a high tide and not as low a low tide. Another effect is the precession of the equinoxes, or the precession of Earth's axis of rotation. As you can see from what we've been looking at for the seasons, Earth's north is always pointing in the same direction. Year by year, that's pretty true. But if you're looking over many hundreds of years, that's not true at all. As a result of the lunar effect on Earth's bulge, Earth itself precesses as a huge top, a huge gyro, a huge dreidel, whichever you prefer. As a result, Earth's North Star used to be Tuban and will be Vega, and in 26,000 years will again be our regular North Star Polaris. Now let's see what that effect does to our North Star. As we stated fairly early on, if we look north at about your latitude above the horizon, you will see Polaris, the North Star. If you were on Earth's North Star, Polaris will be right above your head. In this picture, you see how to find Polaris, the North Star, by looking at the Big Dipper and some constellations in that direction. Now, what would that swiveling motion do to the North Star? More on that in the next slide. The consequences of Earth's axis of rotation precession is that the North Star today is not going to be the same as it is in a few thousand years. About 5,000 years ago, the ancient Egyptians recorded the star Thuban as the pole star, or their Polaris, their North Star. In 13,000 years, the pole star will be very nearly Vega. In 26,000 years, Polaris would be exactly our pole star again. So, from season to season, from year to year, in a human lifetime, Polaris is still going to be our North Star. But in a matter of thousands of years, the North Star does precession in the heavens. Look at this picture below. This is a picture of where the vernal equinox, that is, where the sun is, in what constellation in the sky. If, of course, the day sky was dark, we would see the sun not exactly in the March constellation of Pisces, but actually a little bit towards the February constellation of Aquarius. You may recall that the sun rises with Taurus the Bull in May, with Gemini in June, etc. Now that was exactly true 2,000 years ago, when horoscope became big, when the religion of astrology became really big. That's when it began. It is no longer true now. The vernal equinox was in the middle of Pisces, and now it is going towards Aquarius. In 13,000 years, the vernal equinox will be in Virgo. The constellation of Taurus will rise with the sun in November. That is the other reason that's the other result of the precession of Earth's axis of rotation. This is called the precession of the equinoxes, and was actually known to Hipparchus, an astronomer, at 200 BC. Something that was not as well known is the effect of the moon and the sun working together, or not exactly together, on that precession. Now remember, there are two effects here. One is that sometimes the sun and the moon work together on trying to straighten up the earth, and sometimes not exactly together, therefore not as effectively. And the other is that sometimes the sun is the closest to the earth, because earth is closest to the sun in its ellipse, and the moon is closest to the earth in its ellipse, and that's when you get the most effect. And if it's not exactly in that peak, then you get the least effect. Both of those together make that precession not exactly circular in the sky, and more on that in the next slide. That picture in the sky that was supposed to be a circle has slight nutation, or slight waltzing motion, as you go around in the circles. So basically this is that motion of the pole star as a function of time. Those little loops are greatly exaggerated here, it's very nearly a circle. Those little changes are in matter of arc seconds, whereas the actual tilt of Earth, meaning the whole radius of this circle, is 23.5 degrees. When you look at each and every little waltz, there's also little waltzing in the waltzing, and that's the result of that elliptical motion I was discussing before. And you can see that that has a little bit of an effect as well. So if an astronomer looks and finds what the true north really is, and looks over many years, they would see both this precession of the pole star and the nutation of the pole star. This is the end of the effects that already were discussed by Newton in his great book Principia, that described the physics, how it works for celestial objects, and therefore the invention of astrophysics.